Hey everyone, you're watching the Space Channel. The speed of light blows the human mind. A photon racing at about 300,000 kilometers per second, roughly 186,000 miles per second, takes a little over 8 minutes to travel from the sun's surface to Earth. That's about 150 million kilometers, approximately 93 million miles. But on slightly larger cosmic scales, that's actually not very fast. Take the distances to our nearest stars, Proxima Centauri, Barnard's star, or Sirius. Light from them takes several years to reach us. And if we want to go to far-off star systems, or even galaxies that are thousands or millions of light years away, moving faster than light would be the only practical option. But doesn't that violate relativity? In the late 20th century, a device was proposed that could travel at speeds approaching, or even exceeding, the speed of light. But how is this engine supposed to work? And could it actually be built with today's technology? Let's dive in and figure it out together. The fastest human-made object to date is Helios 2, launched in 1976, which reached a speed of 252,792 kilometers per hour. Approximately 157,000 miles per hour. But that's nowhere near the speed of light. To even get close, we'd need a completely different way of traveling. Basically, we'd have to outsmart space-time itself. General relativity states that space and time are unified, and it explains how mass and energy bend space-time. That curvature of space-time is what we experience as gravity. Science fiction writers have long used this warping as a way to get around the speed of light limit. In 1994, Mexican physicist Miguel Alcubierre showed that compressing space-time in front of a spacecraft while expanding it behind could be mathematically possible, and that it fits within Einstein's general relativity. This principle doesn't break the laws of general relativity, because we wouldn't be moving faster than light. We'd be compressing space-time in front of us. The primary issue with such an engine is that it requires a substantial amount of negative energy density. In other words, we'd need to bend the fabric of space-time the other way, which would take either some form of negative mass or energy, or other exotic matter. For this reason, warp drives are still considered non-physical for now. That said, theorists are already publishing papers proposing warp drives that wouldn't need any exotic matter. To create negative energy, it's said you'd need an enormous amount of mass to produce an imbalance between particles and antiparticles. That imbalance results in a negative energy density. A warp drive would use this negative energy to form a space-time bubble. But according to the calculations, to generate enough negative energy to warp a 100-meter bubble, we'd need nothing less than the mass of the entire observable universe. Other researchers calculated that the required mass could be much smaller, down to roughly the mass of the Sun. Still others argue that negative energy isn't needed at all and propose their own mathematical models. However, neither the first nor the second set of models can be tested experimentally for now. Despite its non-physical status, NASA labs ran experiments with a warp interferometer back in 2012, but the results were inconclusive. All right, let's imagine we somehow managed to warp space-time, whether using negative energy or dark energy. The Alcubierre bubble forms and can travel faster than the speed of light. What happens next? When you travel faster than light, you run into another problem that likely can't be solved: cause and effect breakdowns. In special relativity, simultaneity is relative. It depends on the observer's frame of reference. If a warp drive could accelerate to superluminal speeds, you could get paradoxes where an effect appears before its cause. In other words, your knee hurts first, and only afterward do you fall down the stairs. You could even send something into the past. Here's an example. Let's say someone uses a warp drive to shuttle between Earth and a rocket that's moving back and forth at faster than light speed. The rocket's clock is synchronized with Earth's. However, Remember that, according to special relativity, time on the missile passes more slowly than on Earth. Suppose it's 4 o'clock on Earth when the warp drive departs and instantly arrives at the rocket, where the clock still reads 2 o'clock. Now switch to the rocket's frame, in which Earth is receding faster than light. 2 hours later, they send the warp drive back on the missile, so at 4 o'clock rocket time, but that corresponds to only 2 o'clock on Earth. Here's the paradox. The warp drive returns before it even leaves. At that point, travel through space becomes travel through time. If you build a warp drive that moves faster than light, you've essentially built a time machine. Convenient, but in conflict with all known laws, especially causality. In the case of superluminal travel with a warp drive, there's another issue besides causality: the event horizon problem. It turns out that when the bubble moves faster than the speed of light, the metric becomes singular, similar to that of a black hole. Two horizons appear, a positive and a negative one, equivalent to the event horizons of a black hole and a white hole. In essence, spacetime is warped, resulting in the formation of a black hole and a white hole, each with its own horizon. It's hard to fully imagine the properties of these horizons. Still, one thing is clear. They would prevent the warp drive crew from controlling how matter or energy is distributed to specific regions of the bubble. That would undermine the bubble's stability, because no light signal could be emitted out of a black hole horizon, and none could enter past a white hole horizon. Along with this, those horizons would trigger an intriguing quantum effect: Hawking radiation. Let's figure out what kind of radiation would appear near the horizons. It would be similar to black hole radiation and would have the thermal blackbody spectrum. Theoretical calculations show that the radiation depends on the thickness of the bubble's walls. If the walls were fragile, on the order of the Planck length, about 10 to the minus 35 meters, then the radiation temperature would be about 2 orders of magnitude below the Planck temperature, on the order of about 10 to the 30 Kelvin. Clearly, nothing could remain stable inside the bubble at such a temperature. But if we use a different space-time distortion, one in which, even at speeds several times faster than light, the bubble walls remain fairly thick, then the radiation can be minimized to a temperature near absolute zero, on the order of about 1 millikelvin. The wavelength of this radiation would be a few meters, placing it in the ultra-short-wave radio range. That's better. But how do we deal with causality? Either way, such exotic space-time curvature and the very existence of warp drives remains purely hypothetical for now. So faster-than-light travel lives only in the imaginations of science fiction writers. That's all for now. If you enjoyed the video, please like and subscribe to the channel. See you next time.